In this video, Colin Heathfield from Cole Palmer is going to be talking about diaphragm pumps. So Colin, when would you consider a diaphragm pump?
Theo, thank you for asking me that question. A diaphragm pump is a very good basic sort of pump. Very effective, tried and tested technology. The only moving parts within them are a diaphragm and the valve arrangement. They are true self-priming pumps. So if you need to lift your liquid, if you need to move your liquid, they are set up and can stand alone, and they can be very, very controllable. So they are the biggest part of the positive displacement pump market. They are a very, very popular type of pump because they are basic, because they are very easy to use. In terms of liquids, we would look at waters and water dosing. For instance, a swimming pool. A swimming pool needs to be maintained at critical chemical levels because you don't want to hurt the occupants, but you also need to add liquids, chlorine essentially, and things like that to ensure that the water is safe for them to use. So you would use a diaphragm pump to pump that. And you can use it to react to what we call a pH probe or something to check the acidity of the water and add the liquid. So that's one example. From that end, they also go to the other end where you can check on pump sludges. So thick slurries, I define sludges and slurries. You have water at one end of the scale, and sludges and slurries are anything from soups to thicker, to sort of not quite toothpaste-like, but some thick sort of, such as products used in baking industry, dog food, things like that. If you were to make dog biscuits as an example, you have quite a thick slurry in there, and they can move that. They will pulse, which is one of the things they do, but they are very, very good.
Okay, so what exactly is it? So you've talked about the processes, but what exactly is a diaphragm pump and how does it work?
A diaphragm pump, very basic. You have a diaphragm.
Yep.
We have an example on the table. If you look at this pump, you will see there is a slightly white crinkly line in the front of it.
This one here?
Yes, that is the diaphragm.
Right.
This is a small dosing pump. With bigger pumps it gets much larger. The diaphragm is essentially a round disc of a flexible material. If we look at the screen, we will see there is a diaphragm. You will see there's an orange and a white area. So the orange is the liquid we're pumping. The white area is the area behind the diaphragm.
Right.
The diaphragm is that round disc from a side view.
Yeah.
And then there is a shaft that pulls it backwards and forwards within that chamber.
Okay. So this cream bit here, this is the diaphragm.
That's the diaphragm, is that line there.
Right, understood.
That sort of centre line that's moving backwards and forwards.
Okay.
And essentially, you're just moving that big disc backwards and forwards within a chamber. And within that chamber, as you pull it in, you lift a valve, you pull a liquid in. This orange is the liquid.
Yeah.
So we have a suction stroke and a discharge stroke. We have a suction side and a discharge side. As you pull the diaphragm back in the chamber, there is a valve arrangement at the top. And this is a ball valve here. And the ball valve, as you suck back, so wait till we go on to the suction stroke, sits so tightly in its seal. As it's pulling back, it lifts the bottom ball valve and the liquid flows into the chamber. So you see the orange liquid flowing in, the bottom valve is up. Once it's sucked all that liquid in, so it's pulled back into the chamber and pulled its liquid in, it then goes on the forward stroke. That forward stroke, the bottom ball valve sits down into its seal. So if you imagine a tight circle, the ball sits in that, nothing will pass, and it pushes the liquid out the top ball valve. That is the basic principle of operation. Sometimes you can have a double diaphragm, where you will have the shaft is pulling one, it'll be pushing another, so making more effective use of it. They can be electrically driven, they can be air driven. They are very, very good at what they do. And what they do is a very basic operation, but they can do it very well in terms of control. You can vary the length of that stroke. So if you think you've got a diaphragm chamber that's got a finite volume, you've got a defined volume. If you adjust the amount you pull the diaphragm backwards and forwards in that chamber, you can change the amount, the volume you're pumping each time, but you can control that very accurately. Or you can move that diaphragm more times and pump more liquid, so you can increase the flow rate you can pump with it. They are very, very good at, we talked about swimming pools, so chemical dosing, and they're used widely within other areas of the chemical industry. They're also very good for some crystalline things, and I say that if you're looking at something like sodium hydroxide, which is widely used within the water industry. Occasionally you can get what we call crystallization, which is little crystal lumps forming in the liquid. They can move that past them without too much damage. They don't like abrasives because it will wear the valve areas. I said there was the ball areas. The abrasives, if you had silica sand in there, as the liquid comes past that ball area, it accelerates. It's quite a large amount of liquid to go through a small area, and it will wear the ball valves away. There is other versions. Instead of having ball valves, sometimes they will have what we call a flap valve. So it's just literally, you would have a ring, and your hand would sit on top of that like a flap, and as it pushes, the flap lifts and the liquid comes out. As it pulls, the flap shuts. They are very easy to utilise in that respect.
Okay. Now tell us more about dosing control.
Dosing control. This is, as I was talking about the shaft movement, so you can adjust that shaft movement, how far it goes. You can use that to create your pocket size, your dosing size. So each time you dose, you can dose sort of 50 mil, 150 mil, whatever you set it to. If you were to then gear that to a system, you know you're putting in that amount each time. If your main system went faster, if you were dosing into a line, you could just increase the speed, the number of pockets it's pushing through. So you can set a finite dosing volume, and then you can put it in more or less times. So you've got two ways of controlling what they can actually do. And again, that works if you're adding something to a process. They're also very, very good at transfer duty. Transfer duty where you don't need so much accurate control. Within a lot of industry, they use things like what we call IBCs, which is a large bulk container. And if you want to empty that IBC into your tank on site, you can use a diaphragm pump for that. Very good if you're looking at solvents, because they can be in plastic variants, they can be air driven, so they can meet explosive requirements, and they can dry run to a certain amount. They can achieve good pressures, and these days you can get diaphragm pumps with stainless steel diaphragms. People think, how does that work?
Yeah.
It's incredible, but you can get it so it can move, so you can get tremendous pressures out of them. Those pressures with the flow rate mean they can cover a lot of areas. What they do is they use a stainless steel. It's not a flat sheet, it's got a sort of corrugated appearance to it, so it allows some movement, but it's again on the smaller side, so it's smaller flow rates and achieve the higher pressures.
Okay, and what about maintenance?
Maintenance is very, very basic. If I go to the next slide, and then what we've done in this, we've split the process that I've talked about into 4 parts. So you can see that it's the basic action it's got. The maintenance is very easy because the wearing parts are the diaphragm, because that's a moving item, and the ball valves. The ball valves do wear, and the chamber they're in will wear because that ball is thumping up and down frequently, and the diaphragm wears. They are a back to bench to work on. By back to bench, you've got to take them back to a workbench. You can't leave them in situ and do it. You need to take them out of situ. But then you replace the diaphragm and the balls. So they are very easy to maintain with a basic toolkit. There is no specialist tools per se that you really need. So they're very easy to set up and work on. This is advantageous in the jobs they do. If they're outside in a dirty environment, or you can get stainless ones you can clean down, but there's not much clean down to them. They're very easy to clean down. And as I say, with the drives, with the powers you can get with them, so you can have the electric drive, which will give tremendous control. You can have the air drive, which is very basic, and a lot of industrial sites have air all over the site. So you can just plug and go almost. So you have a very portable unit. They do go up to 3-inch in size, which is a big pump. There can be a cost implication in terms of they're quite cheap to purchase relatively, but the air-driven ones can be expensive to run because you've got to produce air to put into the pump to then use.
Right.
And you're using, there's a volume for volume, you're using a lot of air. But if it's an explosion-proof area where you're moving solvents, then that's what you need to do. So these are all technology considerations for the type of pump you're picking.
Yeah.
So very, very critical. The diaphragms, I think I should mention, they tend to be a rubber-backed diaphragm, but they can be PTFE-faced, so they can handle solvents. PTFE is a very, very inert plastic. There is other options as well for more basic ones using, as I say, a neoprene rubber-based diaphragm, which will give a better service life. But the units can be made from stainless steel, from plastic, and within the plastics there's many variants from polypropylene, PVC. There is PTFE variants, which is the one I just mentioned about in terms of being very, very inert. There's a cost implication for it.
Yeah.
Stainless steel, cast iron. So they can cover the food industry as well, because that design, if we sort of drop back to this, is a very basic design and easy to clean and flush through. If I just go to the sort of the final whys and wherefores.
I was going to say, what are the strengths? Because we've always covered the strengths in most of these presentation videos.
Perfect. The strengths are that variety of materials of construction. As I was saying, because you've got so many different types of materials.
So it makes it versatile.
Yes, so you can cover different liquids, from your water to your solvents to your chemicals. And it's these chemicals and solvents. You know, people think stainless steel is the be-all and end-all, but if you have sulfuric acid at a high temperature and sort of 3/4 purity, it'll leak through stainless steel. Seawater. Stainless steel doesn't like seawater, or you know, so you need a plastic or something else. So you can have many, many materials, and as I say, we're covering from metals to plastics, which allow that great variation. Repeatability is a big thing, and ease of maintenance. Even though it's back to the workbench, it's very easy to maintain. Anyone who's done any DIY would also have the same skills necessary to strip one down and rebuild it. There's nothing complicated. The possible limitations, they do pulse, so there is pulsation. You can have clogging of valves if you're not careful, but they do a very, very good job, very well. As a quick recap, we're good for chemical transfer, good for dosing, very, very widely used in dosing and water dosing. The one I didn't mention, thank you for raising that, is remote operation. Very, very effective, because you can set them up and leave them there, and it just keeps running and does the amount. So if you were to sample something, if you were to be sampling river water, something like that, you could leave it there just pulling a sample through, and it would happily do that and not be affected by pulling a bit of dirt and debris through. One example I talk about sometimes is vegetable soup. Because if you have vegetable soup, you like vegetable soup with, I like it with lumps of carrots in and pieces of peas and things like that. If you put it through the wrong sort of pump, you'll end up with a puree.
Right.
Destroys your soup.
Yeah.
Whereas if you use a big double diaphragm pump, and this is one of the applications I've done many years ago, pulled the soup through, having cooked to put it into other containers before they went to the canning, and it was fine, it came through. And it was absolutely fine. I think one time we even pumped Brussels sprouts, and although there was slight damage on the edge of them, the quality of the sprout coming through after being cooked was fine.
Great.
Because it's what we call a soft solid, so it worked its way, you know, it came through that ball valve. So the selection of the pump is very, very important, and they are a very versatile pump. But this is why they are currently such a large part of the market for the positive displacement pump.
Superb.
Thank you very much.
Fantastic. So that's Colin Heathfield from Cole Palmer telling us all about diaphragm pumps. Thank you very much for sharing that. And if anybody has any questions, just give Cole Palmer a ring, because they have a wealth of knowledge they can share with you.